All right, we're back with part two. Do some short answer questions here. We've got the other two videos with the multiple choice questions, and now we're moving on to short answers. This is going to be technically parts B2 and C1 for some reason. I don't know why it's divided up like that. Just call it part two questions. It's all short answers, and there are 35 of them. So let's get right into it. I'm in the one of the temporary library rooms, which I maintain will be a great band name, temporary library. And it's about 17 degrees in this room, so hopefully that's cold enough to keep me awake. And let's see how we do with this. 51. Explain, in terms of neutrons and protons, why P32 and P31 are different isotopes of phosphorus. Well, obviously they're both phosphorus because it says P and P. This is another of these, or I shouldn't say another one, I don't think we've seen this so far yet, but it's an example of in terms of question. So make sure my pen is working there. In terms of. Anytime you see a question that says in terms of, I'm going to put a box around it right there because we know we need to answer it in terms of this thing. If it says in terms of neutrons and protons, you must make sure to answer your question mentioning neutrons and protons, or you're not going to get any chance of points for this question. If you say something that's completely correct, but you do not mention neutrons and protons, sorry, it doesn't matter. You didn't answer the question in terms of the way they wanted it, so you're not going to get the points for it. So in terms of neutrons and protons, why are these isotopes of phosphorus? Well, I mean, we know it's phosphorus because it says P here and P here. If you remember what the word isotope means, great. An isotope is a different version of the same element, so this would mean it's two versions of phosphorus. One has a mass of 32, one has a mass of 31. That's what that means. P31 means the version of phosphorus that weighs 32. P31 means the version of phosphorus that weighs 31. So they're both the same element. That's going to give us the same number of protons. Phosphorus always has to have the same number of protons. Every element is defined by its number of protons. And the fact that this one weighs 32, this one weighs 31, means they're a little bit different in weight. So what does that? Protons and neutrons give you weight. If they're the same element but different weight, it has to be that there's a different number of neutrons. That is what it means to be an isotope. Same number of protons, different number of neutrons. I'll try to zoom out a bit before we do the next question. All right, determine the oxidation state for number 52 of chromium in K2CrO4. So K2CrO4. We want to find what the oxidation number of chromium is in this molecule. For oxidation numbers, we can go to our reference table, and they're always listed up top. That's where you've seen the charges you've seen during the year. It says selected oxidation states. Typically, it'll be on here. It says selected, so that's kind of a cop-out in case there's ever a number that's not technically on the reference table, but normally it will be on the periodic table right there. And we're just going to try to assign some numbers here. Now, there's no charge overall, so we know it has to add up to 0, but each of these will have their own oxidation charge, oxidation state, so that they can attract each other. So there'll be some positives, some negatives, but they will add up to 0 overall. I'm going to go through and see, do any of these elements have a rule where it has to be a certain number? Because it looks like we're going to have to figure out chromium using them. So I'll start with K because that's the first one. And when I look for K, K right here tells me the only option that we've got is +1. That means each of these potassiums is going to be +1. So I'm going to circle that. That's the important number. Now there are 2 potassiums. So overall, there'll be +2 for that part of the molecule. I can draw a little line here, kind of split up. For oxygen, if I go look for oxygen, it tells me that oxygen has to be a -2. So that again means each of the oxygens has to be a -2. Now there are 4 oxygens, so for the whole oxygen part of the molecule, that'll be a -8. So we have -8 from the oxygen part of the molecule, +2 from the potassium side of the molecule, -8 and +2 add up to -6. This chromium right here has to be some number that when you add it to -6 gives you 0. So chromium is going to be a +6. And that's the number we care about. So +6 is my answer for chromium. That's the one I would write on my answer sheet. And I can even double check on the reference table, and it says that yes, +6 is one of the options for chromium, so that would make sense. If you didn't remember how to do it like this, just go look up the numbers you know have to be right. And we know K has to be +1. We knew oxygen has to be -2. And then if you really had to, you can just plug these numbers for chromium in. Process of elimination will tell you it's going to be +6. So do it that way if you have to, but that's the best way to do it right there. Next 2 questions refer to this little paragraph here. So these part 2 questions, a lot of times you'll see a diagram, you'll see maybe an equation like down here, you may see a little short reading like this, but it tells us 53 and 54 are going to refer to this thing. So let's give it a look. And it says the first 4 elements in group 14 are carbon, silicon, germanium, and tin. And here they are right here, group 14.
Are you testing or anything in here? Do you mind if I just call?
Okay, quick little detour there from a little interruption, no problem there. But it says the first 4 elements in group 14 are carbon, silicon, germanium, and tin, and we can see them right here in group 14. carbon, silicon, germanium, and tin, confirming that they're actually there. These elements form compounds with chlorine and have similar formulas. Two examples of these formulas are silicon tetrachloride, SiCl4, and germanium tetrachloride, GeCl4. So elements in the same column pair up with chlorine in the same proportions. One of the elements in group 14 with 4 of the chlorines. 53 says, state the general trend in atomic radius as these 4 elements are considered in order of increasing atomic number. In order of increasing atomic number just means as the atomic number goes up. So in that case, we're looking atomic number 6, 14, 32, 50. We're looking down the column. So we want to see what is the pattern, the trend in atomic radius for those 4 elements. So I'm going to list them here. Carbon equals this, silicon equals this, and then it's going to be Ge and Sn. And we're just going to see how big these atoms actually are. They are on the reference table. If you turn to the page, table S right after your periodic table, atomic radius is right there. We've used it before during this test, actually. And let's just look it up. Carbon says it has a radius of 75. Write that down. Silicon tells us it's got a radius of 114. It sure looks like it's increasing so far. Let's confirm that. Ge, germanium. Ge is going to be at the bottom here. If we look at germanium, read over, it says 120, so it's still going up. Sure looks like that's going to be our pattern. And just to finish off, make sure we cover all our bases, tin, Sn, right here on the second page, and it says the atomic radius is 140. So clearly, the atomic radius is increasing, and I'm just going to write that. Radius increases. That is the trend. That is the pattern. From top to bottom, the elements, the atoms of these elements go up. It doesn't ask why. If you're thinking about why, it's because you keep adding more shells, so the atom gets bigger and bigger, but it just asks what is the actual pattern. State the trend, so that's it. Radius increases. State in terms of electron configuration. Here's another in terms of. I have to answer the question and make sure I'm answering in terms of electron configuration. Those numbers on the periodic table, like this, that say 2-4, 2-8-10-2, tells you how the electrons are arranged, where they are, and how many in each ring. In terms of electron configuration, why silicon and germanium both form tetrachloride compounds? So why do silicon and germanium make compounds that are really close to each other? Si with 4 Cls or Ge with 4 Cls? Why do they behave similarly like that? Why would they? And in terms of electron configuration, let's look at the electron configurations for these things. Silicon and germanium are both right here. It says 2-8-4 for silicon and 2-8-18-4 for germanium. What about their electron configurations makes them behave similarly? For things in the same column, it's always that they have the same valence electrons. That last number in line is the important one. Their electron configurations look very similar to each other, just one has an extra ring with some extra electrons in it, but that last number line, the valence electrons, is the important thing. Same number of valence electrons. That's the thing we care about. That's always what's going to make atoms, different elements, behave similarly, act similarly, react similarly to each other. All right. Equation below represents the reaction between ammonia and hydrogen chloride. Ammonia is this one right here, NH3, and hydrogen chloride is HCl. If you could figure it out, again, hydrogen chloride, obviously H and Cl, hydrogen chloride. And they make this thing over there. Explain in terms of distribution of charge. In terms of distribution of charge, we have to talk about how charge is distributed. Is something unbalanced and more balanced? Where are the electrons going in our answer? Why is a molecule of compound 1 going to be polar? So we don't even need to necessarily know what this thing looks like. If you know that NH3 looks kind of like this, it's got an N with 3 H's around it, plus some extra electrons on top, that's great. You could look at this and say, well, not every side is alike, so it's not going to be perfectly symmetrical. Okay, it's got these extra electrons kind of crowd to the side, great. If you don't know what it means, all you got to remember is how symmetry works and how balance and polarity and that kind of stuff works. There's this rule for it, SNAP. I think we may have seen this in the video yesterday. Symmetrical is nonpolar. If something's asymmetrical, it's polar. If we're talking in distribution of charge, why compound 1 is polar? Polar means it has to be asymmetrical. So that means whatever the charge is like in this molecule here, it has to be asymmetrically distributed. I can write that. It's going to be good enough. I'm going to write asymmetrical distribution of charge. I'm making sure I mention distribution of charge. That means the electrons are not exactly the same on each side. There's electrons in bonds on 3 sides, and the one side has these 2 electrons by themselves. It's not perfectly symmetrical. The distribution of charge is asymmetrical. That's a good enough answer. Anything that means that kind of answer is good. Draw a Lewis dot diagram for a molecule of compound 2. We got to draw Cl2. That's compound 2. I'm going to draw that. Now, if you remember what it looks like off the top of your head, great. I don't assume you do. So for these kind of covalent compounds, we have to add up valence electrons. I'm going to go to our periodic table and see that H has 1 valence electron, and Cl on the other side has 7 valence electrons. So 1 plus 7 gives us 8 valence electrons we need to use to draw this molecule. I'm just going to put them next to each other. Actually, I'll draw it down here. Give myself a little more room to do it. We've got an H, and we've got a Cl. I got to connect them. I got to put them up into one molecule. We have 8 valence electrons that we need to use and make sure are accounted for in doing that. Well, right now they're just H and Cl, so I'm going to draw one bond to start to connect them and just make sure they're actually locked into each other. That used 2 electrons because there's 2 electrons in every bond. So of my 8, I've now got 6 left. I'm going to put the next 6 down. H only wants 1 bond. It only needs 2 electrons, so as soon as it has that 1 bond, it's done. Can't fit any more. Cl is going to get the rest of the 6. So I'm going to put 2 on top, 2 over here, and 2 on the bottom. The left side's already taken up by this bond. I'm going to double check all my electrons are there. I start out with 8. I use 1, 2 in the bond, and then this is 3, 4, 5, 6, 7, 8. All my electrons are there. I'm good. I used them all up. I want to make sure everybody has the amount they want. H only wants 2. This H is attached to 1 bond. There's 2 in that bond, so the H is good. Cl, like most elements, wants 8, the octet rule. He's got 1, 2 in the bond, and then 3, 4, 5, 6, 7, 8. He's good. That's what my molecule is going to look like. That's HCl. 57 says identify the 2 types of chemical bonds in the product of this reaction. Anytime talking about 2 types of bonds in something, it's always going to be covalent and ionic. Talked a little bit about metallic bonding too. That's just what's going on inside a metal. Covalent and ionic are your types of bonds. Any question that says which molecule has both covalent and ionic, it's asking you to find something with a polyatomic. Polyatomic ions in molecules have both covalent and ionic. This molecule right here has NH4. That's a polyatomic ion on the reference table. NH4, those atoms right here are bound together by covalent bonds, and then they're attracted to the Cl with an opposite charge by an ionic bond. That's what this is asking about. But this thing right here, if you notice the polyatomic ion, think to yourself, okay, polyatomic ions mean there's going to be covalent and ionic both. That's what this is. If you just are guessing what are 2 types of bonds, well, you're probably going to think of covalent and ionic as your examples of 2 types of bonds too. Question 58 on the next page. You got a little bit of stuff to read here. Turn my answer key over. A sample of helium gas, He, is placed into a rigid cylinder sealed with a movable piston. So the size of the containers are much changing, but it does have a piston that can go up and down to make it a little bit bigger, smaller inside. The temperature of the helium is 25 degrees Celsius, the volume of the helium is 300 milliliters, and the pressure is 0.5 atmospheres. State in terms of average distance between the helium atoms. I got to talk about the distance between helium atoms. Why the density of the gas increases when the piston is pushed farther into the cylinder. What this means is you've got a container like this, and it's got this piston, it's got this kind of top on it, it can push in like an engine, and you've got your molecules all kind of flying around here. And then you're going to push this piston down. You're going to push this thing down, so now it's going to go down to here. You're giving it much less space. So it's asking, why is the density increasing when you do this? Well, it's because they're closer together. That's all it is. Density is how closely and tightly packed things are. If you used to have this much space, now you're pushing down to this much space. The atoms are moving close together. You have less space, so the atoms are going to move close together. Density increases because they don't have as much room to move around. They are closer to each other. That's what's asking. 59. Determine the volume of the helium gas when the pressure is increased to 1.5 atmospheres and the temperature remains at 25. Anytime you have a question like this, it's talking about temperature, pressure, volume, and something's changing. There's only one equation to use, and that's the P1V1 over T1 equals P2V2 over T2 formula, the combined gas law. So we have to see what our actual numbers are. I'm going to zoom out a little bit. There's the bell to end 4th period. And I'll write this down here. 59, I'm going to do at the bottom here. It's going to be P1V1 over T1 equals P2V2 over T2. Let's hope no one's trying to use this room in a couple minutes. We'll find out together though. All right, I'm going to list all my stuff. P1 equals, V1 equals, T1 equals, P2 equals, V2 equals, T2 equals. And we'll fill our numbers in as we read the question. The question said, and it's on top of the page, you can read your own, but it said, say, temperature of the helium is 25 degrees Celsius. Now, we do have to convert to Kelvin to do the question, but I'm going to hold off on that for a second. You have to use Kelvin temperatures in these equations, but I'm going to wait to do that just 1 minute. It says the volume of the helium is 300 milliliters, that's the start, and the pressure is 0.500 atmospheres. All right, and now in the question, it says we're going to determine the volume of the helium gas. So we want the new volume of the helium gas after something changes. So V2 is going to be the thing we're looking for. That's going to be our unknown. It says when the pressure is increased to 1.5 atmospheres, that's our new pressure. I wrote this in the wrong place. Pressure should be up here. One correction. That should be up there. Pressure increases, but the question also says the temperature remains at 25 degrees Celsius. Temperature did not change. So the reason I held off on converting my temperature is because I remember in the question it said temperature remains there. If temperature is going to be constant, we can ignore it in the equation. Anything that's staying constant, you can just cross it off and get rid of it, because we would convert that temperature to Kelvin, but it would still be the temperature in both places. So those numbers would cancel each other out. And I'm just going to completely ignore temperature in my equation. I'm going to get it off here too, cross it off there, and now our equation is only P1 times V1 equals P2 times V2. We have these two numbers, our pressure and volume at the beginning. We have our pressure at the end, and we can use that to find our new volume at the end. So I'm going to plug some numbers in. P1 times V1 is now 0.500 times 300 equals 1.50 times V2. That's my equation. Plug our numbers in. Grab my calculator here. Probably can't see on the screen too well, but 0.5 times 300, that's going to give me 150 equals 1.50 times V2 still. And now I want to get V2 by itself. I'm going to divide by 1.50 over on this side. It's going to cancel out. Divide by 1.50 on the other side. And plug in 150 divided by 1.50 is going to give me a new volume of 100 milliliters. So when we change the conditions,
CC4.
We'll have to just accept the announcements, kind of come with the territory when we're not in my basement. But when the pressure is tripled, the volume gets cut in half. Not in half, but by 3. So it goes from 300 down to 100. You tripled the pressure, so you divide the volume by 3, and that's what your volume ends up being. So the new volume will be 100 milliliters. So that's going to be our answer for number 59. 100 milliliters is your new volume of your container, of your gas. 60. Compare the number of helium atoms in the cylinder at a pressure of 0.5 atmospheres to the number of helium atoms in the cylinder when the pressure is increased to that. It did not say we changed anything about this. This is kind of a trick question. Atoms are staying the same. You didn't change anything. You changed the size of the container. Atoms are exactly the same. We didn't take anything out. We didn't add anything in. The number of atoms is exactly the same. We didn't add gas, we didn't remove gas. It's just they're in a smaller container, they're close together. So number of atoms is the same as it was at the beginning. All right, during a laboratory activity, a student places 21 milliliters of hydrochloric acid solution, HCl, of unknown concentration into a flask. The solution is titrated with 0.125 molar NaOH until the acid is exactly neutralized. The volume of NaOH added is 18.5 milliliters. During this lab activity, appropriate safety equipment is used and safety procedures are followed. That's good to know. A couple key words here. I see neutralized, I see titrated. Those are key words. Titrated tells you what formula to use. This is we're mixing acid and base to make salt and water. We want to know how much acid and how much base are going to be going together. That's going to be our last question we're looking on this page, but we want to know how much of each one we need to balance out. 61 says, explain in terms of ions, we have to talk about ions, why the hydrochloric acid, HCl, can conduct an electric current. Electrolytes conduct electric current when they break apart in water. They have these pieces. HCl is an electrolyte. Acids break apart. We know when acids go into water, they're going to split up. The H will break away from the Cl. The OH of the NaOH will break apart because the base is also an electrolyte, but it's asking about HCl. That will break apart. H and Cl will split, creating not HCl, but it'll split into H plus and Cl minus ions. The hydride ion, hydrogen ion, which will jump onto water potentially and form hydronium, and Cl minus as the negative one. Why can this conduct electric charge? Because now these things have their own charges. So electricity can move really easily through them and with them. So it's because there's these mobile ions. Much like metals can conduct electricity well because they have those electrons moving in their samples of metal, these electrolyte solutions do the same thing. It has these positively and negatively charged things floating around in water, and they can conduct electricity really, really well. All right, number 62. Determine concentration of the HCl solution.
With Grace Benedict, Amelia Perry, Ava Schwam,
In the question, HCl, the acid, only has one H. NaOH, the base, only has one OH. We can just leave it as is. So I'm going to see what numbers I have here. For my molarity of acid, it says, that's what I'm actually going to look for. It says, find the concentration of HCl. So I don't know what the molarity of the acid is. I'm going to leave that as Ma. But the volume of acid, it told me I used 21 milliliters. So I'm going to write that as the VA. Equals molarity of base. I have to have all this stuff now. If I'm looking for Ma, I have to have everything else. So the molarity of base, it says 0.125 molar NaOH. So that's 0.125 is the MB times the volume of base is, what's that, 18.5 milliliters. That's how much the base I actually used. And now I just cross multiply and find that unknown one, not unlike what we did in this question over here. So Ma times 21 is going to equal 0.125 times 18.5. Let's put those numbers in our calculator. I'm going to do 0.125 times 18.5. And that's going to give me 2.3125 on the right side of the equal sign. And still Ma times 21 on the left. That didn't change at all. I want to get Ma by itself. So I'm going to divide by 21. It cancels out. Divide by 21 over here. And Ma is going to be equal to whatever this answer is. So I'm going to do 2.3125 divided by 21. And that gives me an answer. It's going to say 0.110119, yada, yada, yada. Lots big number. I'm not going to write this whole number. I'm looking for the molarity, so I'm just going to see what was the molarity of the other side of the equation and kind of match that. The molarity of the base was 3 numbers after the decimal point, so I'm just going to make the molarity of the acid the same kind of length. So I'm just going to go, again, 3 numbers after the decimal point. I'm going to say this is my Ma. So Ma equals 0.110. I'm going to be happy with that. Next page. Okay, this one we have to use a couple little tricks, little time saver things here. Going to look tougher than it actually is. Table below lists hydronium ion concentration and pH values of 4 different solutions and distilled water. So another acid-base related question. pH value is missing for sample 2. So we've got here 5 samples of stuff. It tells you what the samples are. There are different types of HCl, so different concentrations of NaOH, much like we just saw in the last question. And then we've got some water. It tells you the hydronium ion concentration. Remember, hydronium ion is H3O+. That's the ion that gets produced when the H falls off the acid and jumps onto water. That's a measurement of how strong an acid something is. How much of that hydronium ion concentration, how much hydronium ion do you have as your concentration? If there's more of it, it's a stronger acid, less of it, a weaker acid. pH value, again, it's a way to measure acids and bases. Acids are on the left side of the pH scale. So pH scale goes from 0 to 14. Acids are down here, stronger acids, stronger bases all the way on the right side near 14. And number 7 right in the middle, that's neutral. That's where water is. Acids get weaker as they move towards the middle. Bases get weaker as they move towards the middle from that direction. Number 63 says, determine the pH value of sample 2. How are we supposed to do this? We know our pH of all these different things. How are we supposed to approach this? You may or may not have learned how to calculate a pH value, depending on what chemistry class you took this year. You don't have to know any of this stuff, though. Just look at the numbers. If you get to this point, you're saying, I don't know how to do any of this stuff. How am I supposed to even approach this thing? See what the numbers look like. I've got this one missing number, and everything else is here. So let's compare some stuff. It says concentration 1 times 10 to the minus 1 has pH of 1. Concentration 1 times 10 to the minus 7 has pH of 7. 1 times 10 to the minus 12 has pH of 12. You notice any patterns? 1 times 10 to the minus 13, pH of 13. It sure looks like whatever this pH number is, it matches the exponent on the 10, except that has a minus number. So if it's minus 1 here, pH of 1. If it's minus 7 here, pH of 7. Minus 12 here, pH of 12. Minus 13 here, pH of 13. So if it's a minus 2 right there, my pH is going to be 2. So pH of sample 2 is just 2. No real math involved. Number 64. Identify the ion released by the compound dissolved in sample 4 that allows the compound to be classified as an Arrhenius base. Let's read that again. Identify the ion released by the compound dissolved in sample 4. So here's sample 4. And it's asking what of these ions that dissolves when you put into water lets this thing count as an Arrhenius base. Arrhenius is just the name of the guy who had the theories of what acids and bases are. And if you remember, bases have to release OH minus. And that's your answer right there. NaOH. What is it about bases? Even if you don't remember, go to your reference table. You have your acid-base charts on tables K and L. If I turn to my acid-base charts, here's my bases. Well, what seems to be pretty common in all of these bases right here? OH, OH, OH. That's hydroxide. So if you wrote hydroxide, that works, but you could just easily write OH minus. I'm not sure we would be able to give you points if you wrote OH without the minus, probably not, but that would be worth checking the answer key for in the teacher room. But OH minus, that's the ion. OH will fall off here, OH minus falls off there, and Na plus is the other half, but this is the one that makes it a base. State how many times greater the hydronium ion concentration is in sample 4 than in sample 5. So this, again, we go back to that pH scale. Sample 4 has a pH of 12. Sample 5 has a pH of 13. So I'm only really caring about this far right side of the pH scale. So I'm just going to do a quick little number line for myself here. 10, 11, 12, 13. I'll include 14 also. All right, we want to look at sample 4 compared to sample 5. Sample 4 was 12, so we're looking at 12 compared to 13 in sample 5. How many times greater is hydronium ion concentration? We know hydronium ion is the one that acids give off, so the lower a number is, the more to the left it is on the pH scale, it should have a greater concentration, and it does tell us how much greater is hydronium in pH 12 than 13. So this number here is going to have more hydronium than something with a pH of this number here. You just got to remember how this works. This is a logarithmic scale, so every time you move one pH unit, it's actually a 10 times increase in hydronium as you go to the left, or 10 times decrease as you move to the right. So 12 is only one step to the left of 13. That means it's 10 times stronger concentration of that. So 12 is 10 times more hydronium than 13. All right, pH 13. Something with pH 12 has 10 times more hydronium ions in it than something at pH 13. Number 11, you would have 2 steps from 13, so something at pH 11 has 10 times another 10 is 100 times more hydronium than 13. pH 10 has 10 times 10 times 10, 1,000 times more ions than pH 13, and so on. So if you wrote 10 times, that's good enough for your answer. A little over halfway through. All right, at this point, let's break for a word from our sponsor. Today's sponsor is plastic bears that hold honey. Do you like food that comes in the shape of an animal that would totally eat you if given the chance? Then grab yourself some honey and a plastic bear. Boric acid, H3BO3, is heated to produce tetraboric acid, H2B4O7. That's a lot of stuff. And water. The equation below represents the reaction form tetraboric acid. So you've got this stuff boric acid, you heat it up, you make this stuff tetraboric acid, you release water. This thing broke apart into 2 pieces. The next paragraph says tetraboric acid, right here, is then used to make this stuff borax, which is used as a cleaning agent. Borax, and it gives you the formula, is a hydrate, so it's got water in the molecule. That's why it's this stuff right here. Dot 10H2O means it's this stuff combined with 10 waters, they're attached, with a gram formula mass of 381 grams per mole. So this whole thing right here has a mass of 381 grams per mole. It's nice, and the question actually tells you that. A hydrate is a compound with water within its crystal structure. I just said that. Borax has 10 moles of water for every mole of Na2B4O7. Yep, so it's got one of these Na2B4O7s, and it's attached to 10 waters in a nice little package unit. Question 66 asks, explain why the formula for tetraboric acid is an empirical formula. So this formula right here, tetraboric acid, why is that an empirical formula? You need to remember what empirical formula means. Empirical formula means it's already reduced. It's the simplest ratio of stuff. It's not something where it's just kind of a multiplier of things. It's the smallest ratio, smallest numbers you can get. You cannot simplify this molecule any further. You can't simplify this ratio any further. 2, 4, and 7, no numbers go into those that you could pull out. It's not like if you had let's say like H2O2, something like that, and you say, oh, well, let me reduce the 2's, divide by 2, and now it's just HO, something like that. This molecule right here, 2, 4, and 7, that's the simplest ratio you're going to get. So I'm going to say it's already a simple ratio. Can't be reduced. You can't take any common numbers out of those to simplify it or simplify the ratio at all. 67 says determine the number of moles of boric acid that react in the equation to produce 10 moles of water. You may read this question and say, oh, I have to calculate moles. Let me go find that equation. That's not really what it's asking though. It's saying in this equation, how many moles do you need to do something? This can be a stoichiometry question. Determine the number of moles of boric acid, this stuff right here. So in the equation, it's normally using 4 moles of this stuff. We're going to seemingly change that number a little bit. To react to produce 10 moles of water. So normally we use 4 moles of boric acid, and we're going to get 5 moles of water produced. The question says we want to make 10 moles of water instead. So instead of our normal 5, we now want to make 10 of this stuff. So just look at your equation and say, well, how did I change my recipe? If I normally make 5 and now I want to make 10 instead, it looks like I'm trying to make twice as much as I normally make. So if I want to make twice as much of the product, I have to have used twice as much of the ingredients. So if I'm multiplying 5 by 2 to get 10, I got to multiply everything else by 2. If I multiply this by 2 over here, it means I have to use 8 of the boric acid. That's all it is. If you want to set this up as a ratio, you could. You could say 4 moles normally is what you use over X that you don't know how much boric acid you're going to need. Normally I make 5 of the waters. Now I want to make 10 instead. You normally use 4 to make 5. There's your top numbers. You want to use how much instead to make 10. And you can cross multiply it, find your X. It's going to give you the exact same number, which is 8. 8 moles of boric acid. Show a numerical setup for calculating the mass in grams of a 0.200 mole sample of borax. Now you have to actually do a calculation. The good thing is it says show a numerical setup. So you don't actually have to do the math. You just have to plug the numbers in and show how you would do the math if you were going to. So for 68, it says we're going to find the mass of something in grams, and it tells us how many moles. There's only one formula that's going to help us do that. That's the mole calculation. So we go to the back page. If you remember anything about moles, you're going to go to this formula. Moles equals the given mass, how much you have of something, divided by the gram formula mass, how much 1 mole that whole thing actually weighs. So moles equals mass in grams over gram formula mass. We're calculating the mass, so we're trying to find that. So that's going to be our unknown of a 0.200 mole sample. So that's going to be our moles. 0.200 is our moles. Equals, we don't know how heavy this stuff is. We're going to figure that out. And we need to know the gram formula mass. We need to know how heavy this stuff is. Well, let's say it's borax that we're looking for. We want to know how heavy is 1 mole of borax. I don't even know what borax looks like. So let's go check the question. It's probably in there. It doesn't say borax up here anywhere. Let's read through this part again. Borohydrate. Borax right there. This stuff is a hydrate with a gram formula mass right there of 381. You could go and add up 2 NAs and a B and 4 of them, 7 oxygens. No, it says right here, gram formula mass is 381 grams. Thank you very much. I'm going to write that number right there. 381 grams in every mole of borax. Each mole of borax weighs 381. If we had 2 moles, it would weigh twice that amount. If we had 10 moles, it would weigh 10 times this amount. We only have 0.2 moles, so we're going to multiply those two numbers. That's going to tell us exactly how heavy the sample is. We don't even have to, though. The question just says, show a numerical setup. This is all you need to do. If you do answer the question and get answered, great. Even if you got it wrong, it wouldn't matter. As long as you have this stuff right here, 0.200 equals mass over 381, that's all you got to show. This is good enough for a point, and we'll move on to the next question. Question 69. Oh, let's read the top part first. We've got this little setup here. During a laboratory activity, appropriate safety equipment is used. Great. We're going to heat up some candle wax, burn candle wax, I should say. Heat of combustion is defined as the amount of heat released when a known mass of a substance is burned and can be measured in joules per gram. At the start of the activity, the mass of the candle and the mass of the water are measured. The starting temperature of the water is 5 degrees, and the air temperature of the room is 22 degrees. The candle is lit, the water is stirred with a stirring rod, Several minutes later, the candle is extinguished and the student measures the temperature of the water in the can. So it looks like you're going to put water in this can, you're going to burn your candle, the candle will heat up the water, and the water is going to get hotter at some point. When the candle is cool, the student measures the final mass of the candle, so you can always see then how much candle you had to burn in order to heat up the water by however much it was. And you got this nice little table here. It shows the mass of the candle wax burned, the mass of the water in the can, the temperature change of the water. So water looks like heated up by 39 degrees as you had the candle underneath it. How much heat was absorbed by the water, we don't know. And the heat of combustion of candle wax, that's a constant. So on the periodic table or the reference table, it gives you the heat of fusion, heat of vaporization, these constants for water. This is the specific amount of heat you need to give candle wax in order to make it actually burn. Question 69 says, state the number of significant figures used to express the value for the mass of the water in the can. So no math, we just have to see how many sig figs in a number. The value for the mass of water in the can. So let's find mass of water in the can, and there we go. It's asking us about this number right here, 190 with a decimal after it. So if you remember your significant figure rules, if decimal is present, which it is, P for present, P for Pacific, we're going to read from the left to the right. That's the Pacific Ocean side. We ignore any zeros we see first, and then once we see a non-zero digit, that number and every number after it is significant. In this case, the first number we see is a 1, so that 1 and everything all the way to the end are all significant. So that's 1, 2, 3 digits that are all significant. In a number like this, if we started from the left, we would have ignored that 0 first, and then just the 8 and the 3 would be significant. Number over here, there is no decimal, so we would say the decimal is absent. We'd read it from the Atlantic side, and we would ignore all these zeros until we got to the 7, and the 3 and the 7 would be significant. But in this case, it's 3 sig figs. 70 says, state the direction of heat flow between the air and the water in the can before the candle is lit. So before the candle is even lit, let's go see what was going on here. I see right here it says the candle is lit. So I'm going to see before that even happens what was going on with the heat before that point. It says state direction of heat flow. We just have to say which direction heat's moving. Heat always moves from a higher temperature to a lower temperature. So the starting temperature of the water is 5 degrees and the air temperature is 22 degrees. So what's a higher temperature, 5 degrees or 22 degrees? The air is hotter, 22 degrees, so it'll send heat energy to the water at 5 degrees. So I'm just going to say air to water, and that's good enough. If you want to write a whole sentence, whatever, if you want to write 22 degrees going to 5 degrees, something like that, the direction is going from the air to the water before you heat it up. Last question on the page, 71 says determine the amount of heat absorbed by the water. All right, we know we gave the water some amount of heat, and that was able to heat it up by 39 degrees. That's all we know happened here. So we can use an equation to figure this out, and it's based on you heated the water up. We don't have any kind of equation for combustion. We just want to see how hot do we get that water and how do we do this. We have our heat calculations on the back page of the reference table. And there's 3 formulas, Q equals MC delta T, Q equals MHF, Q equals MHV. The only one that says anything about temperature change is this right here. Q equals MC delta T, that's the only time you can use this equation is when you have a temperature change. It gives the delta T because that's what it's talking about. If you try to use these equations with change of temperature, you're not going to have the right information. M is mass, and then HF or HV are just these constants. It says nothing about temperature change. So this is the one we're going to use right here. So Q equals MC delta T, and we have to plug some numbers in here. It's water we're talking about. We're trying to figure out how much heat it absorbed. Heat is Q, so Q is what we're going to leave blank. That's what we're going to look for. M is the mass of water, so I can go back up and see how much water we actually had. It tells us right here, mass of the water is 190 grams of water. C is a constant. That's on the reference table. It's how much energy does water need to absorb in order to change temperature. That is the specific heat capacity. So it's this number right here. As long as it's water, it's 4.18. The formulas are on the back of the reference table. The constants are on the front of the reference table. And then delta T is the temperature change. How much did the temperature of water change? It tells us right here it changed by 39 degrees. So I'm just going to write 39. So this much water, each gram of water heated up by 39 degrees. If you've got 190 grams of water, multiply those numbers out, and each one of them required this much energy in order to change it by 1 degree. So multiply these two numbers. I'm going to go to my calculator. I'm going to plug in 190 times 4.18 times 39, and I get a big number. I'm going to make sure it's the same number I had on my page right there, and it is. It says this is going to be 30973.8. I'm going to leave it as that number. You could round it off. You want to do 30974 without work. It's not some long decimal. I'm just going to leave it exactly like that. And then anyone grading this test would know I knew exactly what I was doing. And if you want to write kilojoules as a unit, it's probably going to be printed on your answer key anyway. But that's how much heat you need to heat up water and change the temperature by 39 degrees if you had 190 grams of that water. '72. We've got about 13 or 14 questions left, and looking at the time, got about 17 minutes left, so that's actually maybe perfect. We'll see if we get this video done. If not, I may have to pause and do it later, but let's see how we do with these. A process was developed in 1912 to produce ammonia gas from atmospheric nitrogen. So there's your ammonia gas made from nitrogen and hydrogen. Iron can be used as a catalyst. The equation representing this system is shown below. State evidence from the equation that the forward reaction is exothermic. What does exothermic mean? Exo, like exit, heat is going out. So we want to show evidence from this equation. So it's all in here somewhere. It's telling us evidence from the equation that the forward reaction is going to be exothermic. Exothermic means you're losing heat. So it's just because the heat's over here. I'm going to write heat on right of arrow. As long as the energy is on the right side of the arrow, that means it's exothermic. You're releasing this energy as one of the products. Compare the rate of the forward reaction to the rate of the reverse reaction, and it says at equilibrium. Equilibrium means the reactants are being converted into products at the exact same speed that the products are breaking apart again into reactants. So N2 and H2 are combining and reshuffling into NH3 at the exact same speed that NH3 is breaking apart into its original pieces N2 and H2. So you don't see any big change overall. So compare the rates of the forward and reverse reactions. The rates are equal. The forward reaction and the reverse reaction happen at the exact same speed, so they cancel each other out, and you don't see any overall change in the amounts of reactants or products. Number 74. On the labeled axes in your answer booklet, so in your answer booklet you would have a little blank graph like this. It would say time this way, and then you'll have potential energy on the other axis like this. On this labeled axis, draw a potential energy diagram for the forward reaction presented in this equation. You don't have numbers here. You don't even know how much the energy changed by. All you know is energy was released. So you just have to draw a very simple curve that shows energy being released. Remember the potential energy diagrams, they always look either flat like this, they go up the hill and then they drop down, or they start flat like this, go up the hill, and they finish up higher than where they started. Either one of those shapes. In this event, the energy is being released, so you're losing energy. It's going to be something like this. Just draw a picture like this. A flat line, and then you go up the curve, and then you drop down again. As long as you've got a flat section, up the curve, drop back down again, and end up lower than where you started, that works. Do not draw something like this, where they look even. That is not how it looks. You're never going to see a picture like this that goes upside down. That's not how it works. You need that roller coaster hill to go up, and then drop down. In this case, it's going to end up well below where you started. If it was gaining energy, it would have finished here higher than where it started. So this is what you want to draw for 74, something just like that. 75 is in terms of. State in terms of moles of gases why the equilibrium shifts to the right due to an increase in pressure on the system at constant temperature. So if it's shifting to the right, an increase in pressure will shift it to the right. So it tells us we have to answer in terms of moles of gases. So why would increasing pressure make this thing go that way? Well, it says in terms of moles of gases. Let's see what we actually have. We've got 1 mole of N2. There's no number here, but will be a 1. So a mole of N2 and 3 moles of H2. So that's 4 moles on the left side in the reactants. And on the right side, I see a 2. So that's only 2 moles of NH3. This is just energy. It doesn't count as moles. So why would increasing pressure make it shift in the direction that's going to have fewer moles of gas? Well, think of it. If you have a container with more pressure, you're going to try to force things in. It's going to be easier to fit 2 moles into that space than 4 moles into that space. So you can write, in terms of moles of gases, fewer moles of gas in the products. There's fewer moles this way, They're going to be easier to fit into a pressurized thing than 4 moles. 76. State what happens to the rate of the forward reaction when iron is added to the system. Do we know anything about iron? I don't see iron written here anywhere. Up here, though, it says iron can be used as a catalyst. So it's really asking, how does this catalyst impact the rate of the forward reaction? Catalysts speed stuff up. So I'm going to say rate increases. That's what it is. Catalysts make things go quicker. They give it a faster pathway. If you're looking at a picture like this, the catalyst is the one that would make a little dotted line like this that goes kind of under the regular curve. I can't see it on camera too well like this. It doesn't change where you start or where you stop. It changes how you get there. It gives a nice detour, a nice little shortcut for that reaction, but it speeds up the whole reaction. All right, we may have to stop after this next batch of questions. Let's see how we do that. We've got about 12 minutes left. We can probably get through a bunch. Before the year 1828, it was thought that organic compounds were produced only by living organisms, that inorganic compounds were made from non-living substances. Urea is an organic compound, and in 1828, a chemist heated ammonia cyanate and produced urea, which is very soluble in water. The equation below represents the reaction. Ammonium cyanate heated up rearranges to make urea. Identify the element present in urea that's present in all organic compounds. I have seen this question in so many recent tests. What elements in organic compounds? Got to know that. If you forget, you shouldn't, hopefully, because you probably just did organic within the last week. But if you forget, just go to your reference table. You got 2 charts for organic stuff, really 3, but 2 that are going to be important here. Organic prefixes. It's based on number of carbons. That seems like it's probably pretty important. Down here, homologous series. Again, has a bunch of carbons as the main thing. Carbon's your element. It's just asking what elements in organic compounds. That's it. Carbon. Compare the formula mass of the 2 compounds in the equation. Formula mass is how heavy it is. It's like gram formula mass. If you go through and add up what N weighs and what 4 H's weigh and what O weighs and what C weighs and what N weighs, you'll get a mass. You could do that. You could add up what 2 H's and an N and C and O and N and H2 over here weigh. You'll see how heavy this thing is. You'll see how heavy that thing is. They're going to weigh exactly the same. You could save yourself some time because you know this stuff's turning into this stuff, and I don't see anything extra that it broke into a separate piece. I don't see anything extra over here that I added something weird in. I'm just going to check these. I see 1, 2 N's on the left, and I see 1, 2 N's on the right. I see 4 H's over here. 2 plus 2 is 4 H's over here. 1 O, 1 O. These are the exact same things. So yeah, if you add it up, you're going to get the same answer, but the masses are the same. They're the same pieces. They just got rearranged. Same stuff. State in terms of molecular polarity why urea is very soluble in water. In terms of molecular polarity means, is it polar, is it nonpolar? Why would urea be very soluble in water? Soluble means you can dissolve. So why would urea be able to dissolve in water based on whether or not it's polar or nonpolar? Water is polar. If you don't remember that, remember that. Water is always polar. And we have this rule that says like dissolves like. Polar things dissolve in polar things, non-polar things dissolve in non-polar things, and they don't mix. That's why oil and water don't mix, because water is polar, oil is non-polar. So if urea is dissolving in water, and like dissolves like, water is polar, so urea must also be polar. I'm going to write urea is polar like water, but that's all you got to write. Urea is polar. Water is polar, so urea must also be polar. If you wrote like dissolves like, I would want to give you the points. Someone else may argue with me, but write this. Urea is polar. That's why it will dissolve in water, which is also polar. All right, we've got this whole thing here. We've got to think about a voltaic cell. We've got this picture of battery. It gives us the equation here. And I don't think I even need to read the top part because I don't think we need that specifically to answer these questions. We don't. So I'm not even going to bother reading that top part. You should when you're taking the test, but it's not going to exactly help me answer these questions. So I'm going to skip it just to save some time. We've got a picture of the battery. It tells us how it works. And we've got this little chart down here showing us how the voltage of this changes based on how much of the Cu ion is in the liquid. No biggie. Number 80 says, based on the graph, determine the voltage of the cell. So based on this graph, determine the voltage of the cell, which is on the left side over here, if the CuNO3 concentration is 1.5 molar. Let's find 1.5 molar right there. There's 1.5 molar. We're going to go up to the line, and we're going to see what the voltage is. That's it. 1.5, I'm going to go up to here. It's actually got a dot, and I'm just going to follow that number. It looks like it's kind of right here between these two numbers. So it's going to be between 1.10 and 1.11. If you look at that and say, oh, it's probably a 5, It's really not. That would be bigger. Just do an average of these two numbers. I'm going to make sure I get this right. So I'm going to do 1.10 plus 1.11. Those are my two numbers on the chart. I'm going to hit equal. I'm going to divide by 2 to make sure I get exactly what's between those. And it's 1.105. 1.105 is going to be my good answer. It's exactly between 1.10 and 1.11. 81 says write a balanced half reaction equation for the oxidation of zinc that occurs in this cell. It's nice because it gives us the equation right here. It tells us how it works. We want to say the oxidation of zinc going from this version of zinc to that version of zinc. What was the half reaction? So you got to remember, Zn with no charge, that means it has an oxidation number of 0. Zn with a +2, that's oxidation of +2. We want to write how that works. So you're going to Zn 0 going to Zn +2. So I'm going to write Zn going to Zn +2. If you want to write a little 0 here, you can. No need to, but you can. And a balanced half reaction, we have to write electrons in. So how do we go from Zn 0 to Zn +2? How do you get to be a positive charge? It means you had to lose electrons. Remember, to balance out these equations, you always find the more positive side. +2 is a more positive number than 0, so I'm going to write some number of electrons on this side to make sure the charge is balanced. How many electrons with a -1 charge each would I have to give to +2 to bring the charge down to 0? That's going to be 2 electrons, and that's my balanced half reaction right there. This is what happens to zinc. Zinc will lose these electrons, and the copper will end up gaining the same number of 2 electrons to go from +2 to 0, but didn't ask about that. We've got 4 questions left, 1 page left, all nuclear, and looking at the bells, they've got about 6 minutes. So let's see if we can get through these last couple questions. I think we can. Synthetic radioisotopes, so nuclear radioactive things, but they're man-made, may be made by bombarding other nuclides with neutrons. So you fire neutrons at something that's stable already, or at least a little bit unstable, and you make man-made radioactive stuff. The equations below represent a sequence of reactions converting stable iron-58, so it's not radioactive normally, but we can make it radioactive, to cobalt-60, which is used in medical treatments, and it gives you 3 examples of stuff. 82 says state the neutron to proton ratio for an atom of Fe in equation 1. Fe in equation 1, we got to zoom in here and see what Fe looks like in equation 1. And you may not be able to see it well on camera, but it's Fe. I'm going to do this down here. It says Fe with a mass of 58 and atomic number of 26. So mass of 58, atomic number 26. Atomic number is protons. So the question wants to say the neutron to proton ratio. I now know I have 26 protons. To find the neutrons, it's going to be the difference between these two numbers. The mass number is neutrons and protons combined. Atomic number is just protons. So to subtract these two numbers, it'll tell you what your neutrons is, and 58 minus 26 is going to be 32. So I have 32 neutrons and 26 protons. That's our answer to 82. 83 says, state in terms of elements, so we got to address elements, why equation 2 represents a transmutation reaction. What are elements doing here? Transmutation means you're turning one thing into something else. It's not you're moving pieces around, you're making a completely different substance, a completely different element. Iron is turning into cobalt. In terms of elements, one element is turning into another element. I'm going to write that. One element becomes another. You could also write Fe becomes CO. That would work too, but one element is turning to another. In terms of those elements, one thing is turning into something else. It's not just iron matched up with somebody else, it's actually turning into a completely different thing. 4 minutes till the bell, 2 questions left. Identify the particle represented by X in equation 3. So let's write equation 3. I'm going to rewrite it down here. It says CO with a mass of 59 and an atomic number of 27, plus X turns into cobalt with a mass of 60 and an atomic number of 27. I just got to figure out what X is. So we need our top numbers on the left to balance out the top numbers on the right, bottom numbers on the left to balance out the bottom numbers on the right. If our atomic number down here, 27 on the left and 27 on the right, well, they're the same number already. So this right here would have to have an atomic number of 0. On the top, we got 59 on the left and 60 on the right. So 59 plus what will add to 60 on the right. This has to be a 1. So far we have X having a 1 as its mass and 0 as its atomic number. I'm going to go to my nuclear particle chart, table O, and I'm going to see what has a mass of 1 and an atomic number of 0. And that's right here. Mass of 1, atomic number 0, it's a neutron. X is a neutron. I'm going to go back and write neutron for my answer to number 84. Last question. 2 minutes to the bell. Determine the fraction of an original sample of cobalt-60 that remains unchanged after 15.813 years. We're going to have cobalt-60, and we know after that many years, we're going to have some amount of it left. It says it's going to go for 15.813 years. We need to know how long it usually takes cobalt to break down, so I'm going to look that up. Cobalt normally takes 5.271 years for 1 half-life. So I'm going to do the half-life, or the amount of time it tells us, 15.813 years, divided by the half-life of cobalt, 5.271 years, and that's going to give me 3 half-lives. So it's able to break apart 3 times in that time period. It says what fraction remains. So 1/2, 1/4, fraction like that. After no half-lives, before anything has happened, you have a whole. You have an entire amount of stuff. After 1 half-life, we'll see what happens. After 2 and after 3. After 1 half-life, you're going to have half of it left. Big surprise. After another half-life, half a half is you'll have a quarter of it, 1/4 left. After another half-life, and all 3 that we've done, we're only going to have 1/8 of it left. That is your answer. That's how much will actually remain. 1/8 of the original sample will still be cobalt. The other 7/8 will turn into something else. That is 85 questions. That's the entirety of your Regents. And we've got about probably seconds to spare because the clock on here says 1:11. So I need to get to, 6th period class. So I'm going to turn this off right there. Hopefully this helps. Ask any questions of me or any other teacher if it doesn't. And good luck.